mathematically, not numerically. That's what I'm getting at. All right, so let's take a look at this. Problem number 6. Okay, so get back to University of Physics to optimize. All right, this one is really, really colorful. All right, let's get rid of these. Okay. All right, so this is based upon the PowerPoint slide that you guys have seen. All right, so if you vary the magnetic flux, it's going to cause an electromotive force. The electromotive force is going to cause a circulating electric field. All right, put differently, within this area, and the area that you're looking at is this area, you're just simply varying the strength of the magnetic field. So within this area, you're changing the strength of the magnetic field. All right, and then what's happening is by varying the strength of the magnetic field, you're causing a circulating electric field. Once again, as usual, the direction of the integration is always going to be in the counterclockwise direction. All right, if you see this, and it's implied that we will do the integration always in this direction. So electric field EDS is always going to be integrated in the counterclockwise direction. All right, so this is the generalized expression for the Gauss's law. All right, this should be once again vectors for it to make sense. Okay, so we're going to take a look at 2 cases. We're going to be interested in the strength of the electric field inside the radius of this region. All right, so this is the region that you're looking at. Within this region, you're going to vary the strength of the electric field. All right, you're varying the strength of the magnetic field within that region. All right, so let's make a note of it. So this is the region within which we're going to be varying the strength of the magnetic field. All right, so this is your R that we're looking at. Okay, so what this says is, all right, so you got this region. The radius of this region is this, obviously. You're just varying the strength of the magnetic field within this region. When I'm interested in the strength of the electric field, circulating electric field at a radial distance R, which happens to be within this region. All right, so I want to know how the strength of the electric field is going to vary between this point and that point and that point and that point. So what is the strength of the electric field here? R2, R3, R4. So the question is, how does the electric field vary within this region all the way up to the radius of this region? Okay, this is one of those things. If I were to give you a numeric problem, sometimes you guys kind of get the concept in a general sense, but sometimes you guys are not paying attention to the details. That's when you guys usually get into trouble. All right, so here's the formula that we will get to in fully. And we know that the area is going to be constant, so in terms of changing the flux. So what's varying is the strength of the magnetic field. All right, so I'm going to divide this into 2 sections. The first thing that I'm going to focus on is, let's focus on the right-hand side. Okay, so we're varying the strength of the magnetic field within the area. In this case, the area is straightforward. All right, so this area that you're looking at is going to be the area of what? All right, what's responsible for this circulating electric field is the change in flux within the area of this circle that you're looking at, guys. All right, so change in flux outside of this region, outside of the region of small r, is not going to affect the strength of the electric field. All right, I mean, if you're varying the flux within this region, it's not going to affect it. All right, so any variation of the flux within this region is responsible for the circulating electric field. All right, so the area that you're looking at is the area within the region where the electric field is actually changing. All right, I'm not saying it right, but this is, so you're only interested in this region. But if that's the case, the area that you're interested in is going to be pi r squared, so it's going to be related to the lowercase r. All right, on the left-hand side, this ds that we're looking at. All right, so on the ds that you're looking at is going to be the circumference. EDS is going to be E times the circumference of this length. So EDS is going to be 2 pi r. Okay, so this equation is going to turn into this equation. Obviously, you got your cancellations. And then the final equation is going to look like that. Okay, the stuff to emphasize here is when you're looking at a final equation like that, obviously the strength of the electric field is going to be directly related to how fast you're changing the strength of the magnetic field. But the only variable that you have given the change in the magnetic field is your radius. All right, so within this region, all the way to the perimeter of this region, the strength of the magnetic field is going to increase radially. That's what it means. All right, so what that means is the strength of the electric field here is going to be weaker than the strength of the electric field here, and which is going to be weaker than the strength of the electric field here, and all the way up to the radius of this region. All right, so R is your variable. So the strength of the electric field is just going to vary radially. So what's happening is the strength of the electric field is going to increase radially, just like that, all the way up to the radius of that circle. All right, which is the same as this. All right, let's just add to that one. All right, so we need to put a capital R there. All right, so that's case number one. Case number two is straightforward. Now we're interested in the strength of the electric field outside of that region. All right, so the strength of the electric field outside of the region of the change in flux. Okay, so the flux is changing within this region, all the way up to the radius of this region, the circle region. So the question is, what happens to the strength of the circulating electric field outside of this region? How does that vary? Okay, once again, guys, here's the generalized expression. Once again, what's changing is the magnetic field within the area with the radius of capital R. All right, so in this case, the area of capital R is going to be pi r squared, which is going to be responsible for the circulating electric field. And ds is going to be the circumference, which is related to the region outside the region of change in magnetic field. So in this second case, R is going to be larger than capital R, which happens to be smaller. All right, so if that's the case, this ds is going to be 2 pi r. All right, so the equation becomes like that. Obviously, there are cancellations. And then here's the final expression. According to the final expression, the electric field strength is going to diminish inversely as the radial distance once you're outside of this region. All right, so you end up getting the strength of the electric field diminishing outside of that region. Okay, so that's it. It seems like a really abstract concept, and unless you're a physicist, most of you guys wouldn't enjoy this, but out of this, we will have the electromagnetic waves. All right, this is a really, really powerful concept. And the guy who was able to make this connection was Maxwell, Einstein's hero, as you will find out. All right, so Faraday was not able to come up with the mathematics of it because he didn't know how to use math. He got lucky. The Scottish physicist, James Maxwell, became interested in Faraday's work, and he decided to formulate it. Okay, so Maxwell's laws is something that we will discuss next week. It gets slightly more abstract, and then this is going to take us into optics. Okay, so Lenz's law gives you the direction of the induced current, right? All right, so according to the Lenz's law, the current is going to move in a direction that's going to oppose any change of flux. All right, so the current is going to move in a direction that's going to oppose any change of flux. That's what it means. All right, so what purpose does it serve? It tells you the direction of current, induced current, in the Faraday's law. And let's take a look at number 10. It's a bit of a conceptual one. Okay, so we have a loop, which is going to be placed parallel to this paper. So we'll just place it just like that. And the strength of the magnetic field is going to be increasing. All right, so we got a loop just like that, and we keep increasing the strength of the magnetic field. It doesn't say which direction it's increasing. Hold on. Assume that the magnetic field is pointing out of the page. Okay, so we are increasing the strength of the magnetic field. All right, so this is what we got. Here's our loop. Just gonna have a bunch of magnetic field lines. All right, so this is B out of the page. And then this one is gonna be the new one. All right, so let's make this the new one. All right, so I'm increasing the strength of the magnetic field. So what needs to happen is the current needs to move in a direction that's gonna oppose this change. All right, so which means that the induced magnetic field has to oppose this change. So this is going to be the induced one. All right, so which direction does the current need to move? Which direction does the current need to move in order to, Yeah, it needs to be clockwise. Give yourself 2.71. All right, that's it. So the induced current has to move this way. Okay, so this is a nice visual explanation for it. So it needs to move clockwise.